So, good evening, everyone. My name is Abhishek. I welcome you all to the week 9 live interactive session on the NPTEL course Applied Thermodynamics for Engineers. So, I'm a PMRF research scholar from the Department of Mechanical Engineering, IIT Guwahati. And we have already covered previous 8 live interactive sessions where we have discussed various numericals and multiple choice questions based on the lectures that were covered in that previous week by the instructor. Now, if you have any doubt on those previous session or even in this session, you could write a mail on this mail ID, and I will be trying to answer it as soon as possible. And if, for example, if you have missed your lectures and you want to see them again, then you can refer to this NPTEL in this YouTube channel where you can find the recorded version of this lecture. Now let's start. In this week, we have already covered lecture number 22 to 25, where we have discussed various forms of refrigeration cycles, starting with vapor compression refrigeration cycles, where we have discussed triple S cycles and the refrigerants that are used, and some of the modification in this vapor compression refrigeration cycles for enhancing its output. So first of all, to start with vapor compression refrigeration, if you remember, the discussion started with the reverse Carnot cycle. So it was somewhat like this, an ideal Carnot cycle. Throughout the cycle, it stayed inside the dome. This was the Carnot cycle that was discussed, the reverse Carnot cycle that was discussed to generate some out cooling. But if you remember, the discussion was that this cannot be a practical cycle due to various reasons. So first of all, which is like the compression takes place in the wet zone. So a compressor, there cannot be a compressor which can compress both fluid and the gas. Okay, so that is one of the problem. So did someone join? I would request to just mute your mic.
Yes, sir. Done. Good evening, sir.
Good evening. Okay. So based on that, this was one of the problems. And the other problem was when we are going for expansion in the turbine that we are going, that also we see is happening in the wet zone. And this was also one of the reasons why we shifted to Rankine cycle in case of power generating cycles. So based on that, we shifted to slightly modification of this reverse Carnot cycle, and that is the vapor compression cycle, where what we did was the condensation, the evaporation in the evaporator, we extended it towards the vapor saturated vapor line, and after that we did the compression, which is isentropic compression as previous. Sorry, isentropic compression. Okay. Now, as we go outside of the dome, I have already said you that the straight line is the isothermal line, but we can no longer follow the isothermal line, because if you see, this is at a different pressure and this will having a different pressure, the pressure at which the condenser is working. Okay. So here, if we follow the isothermal line, so the both will be having different pressure line, which is not possible. We cannot have two different condenser pressure. Okay, for that, this generally this heat rejection will be taking place at constant pressure process. And then in place of turbine, as we are dealing with liquid, so we have gone with the isenthalpic process. We have gone with the throttling. Now this is the vapor compression cycle that you see, and this is generally used in all the refrigeration cycle that you see around you, even in your AC that you use in your for domestic purpose, even your car AC, and even the central AC that is used in modes. Okay, and this is also known as the triple S cycle. Okay, standard saturated single stage refrigeration cycle. Okay. So based on that, what are the refrigerants that are used were discussed on its nomenclature. If you see, we discussed alkanes. These are generally the hydrocarbons. and these have single bond between the two carbon atoms. Okay, and other thing was the inorganics. Some of the inorganics fluid can also be used as the refrigerants. Then the other thing that was discussed was if it's not inorganic, then mostly we can use mixtures like azeotropes and geotropes, which we discussed, azeotropes and geotropes. And geotropes. Okay. Now, another thing that was not discussed in the lecture, but you can consider is it olefins, even olefins where there is a double bond in carbon, because this type of refrigerant can be found in their generally in the automobile refrigeration cycles. Generally, this olefin is used, and nowadays also more and more olefins are being used because they have the lowest GWP, that is the global warming potential. I think this was also discussed. GWP and ODP, or ozone depletion potential, and the GWP is the global warming potential. These are the two parameters on which these refrigerants are judged. Because if you see the global warming potential is compared with that of CO2. CO2. CO2 is a global warming gas. So CO2's global warming potential is denoted as 1. Now the ratio GWP is calculated by the global warming potential of CO2 and that of that refrigerant. Let us say that is some RXX. So this ratio is actually the GWP. Okay. The same for ODP. ODP also is considered with respect to R11. Now these olefins have carbon double bonds. Okay. Here we have carbon single bond. Here we have carbon double bonds. We'll discuss on its nomenclature. First of all, this alkane we discussed. It is named like mostly you will find it in a 3-digit like R, X, Y, Z. And after that, maybe you will find A or B, and this is generally the isomers, the structure, how it is the chemical formation, the chemical, how is its chemical structure. Now X, if you go with X for alkanes, you see R, X, Y, Z. X is the number of carbon atoms minus 1. Number of carbon atoms minus 1. Okay. Y is the number of hydrogen atoms plus 1. And Z is the number of fluorine atoms. Now, as these are alkanes, you will be having the maximum, the carbon has a maximum bond formation of 4. Each carbon has a bond formation of 4. Okay, so based on that, we have that formula. If there are n number of carbons, so 2n plus 2 is the maximum number of bond that it can form. Okay, so for example, that is the way in how you find in methane. Methane, you have 4 bonds. Okay, so if you want to substitute hydrogen with other atoms like chlorine or fluorine, then you have to substitute this hydrogen with another single bond atoms with chlorine or fluorine. That is the way how this is being named, and I think this has been very well covered in the lectures, so you can refer that. And based on that, we have also discussed R134. R134A. This is the refrigerant you find generally in any of the domestic ACs nowadays. Okay, and I hope you can find out what is its chemical formula. If you see, X is the number of carbon atoms minus 1. So here the number of carbon is how much? If X is equal to 1, so number of carbons will be 2. And then H, how many H you have? H you have 3. 3 means H, number of H is 2. And then fluorine atom is 4. As the number of carbon atom is 2, so how many bond it can form? It can form 6 bonds. From 6, all the 2 hydrogen, 4 fluorine has already been covered. That is why this is C2H2F4. It doesn't have any chlorine, and thus this does not have any ozone depletion potential. That is why this is mostly used in nowadays. Okay. Now the other variation is the olefin. In case of olefin, you will be finding the nomenclature just like there is an additional numbering RAXYZ. 4 digits you can find in there. Now AH stands for the number of double bonds. Okay, and XYZ are the same as that of alkanes. So here what you will find is mostly you will find in your car ACs 1, 2, 3, 4 is used. This is the refrigerant you can find in your ACs, in your automobile air conditioning system. So in here, one means there will be one double bond with carbon. And then the same thing goes for the say 2, 3, 4. 2 means there will be 2 means number of carbon atoms minus 1. So number of carbon atoms here will be 3. Then the number of carbon atom for 3, if 3 it is there, then the hydrogen will be 2 and fluorine will be 4. Okay. And here also you can find out what is the maximum number of bonds that it can form. And from there you can find out how many chlorine atoms it is attached. Okay. Now, other refrigerant was discussed was, for example, ammonia or water. For them, it is generally very simple. You use R7 and the XX, which XX means the molecular weight. For example, if ammonia, then it will be 17. For water, it will be 18. Okay. And for mixtures, azeotrops and geotropes, azeotrops will find as 500 series. And this, the last 2 digits generally refers to its structure or the series. Actually, the 2 different types of mixtures are mixed, different types of compounds are mixed to form this mixture. So what are the mixture and what is its composition can be found out from a table, mostly ASHRAE table, American Society of Heating, Refrigeration and Air Conditioning. Okay. So from this table, you can find out whatever, for example, if I say 514, this corresponding to this 14, there will be a mixture that will tell what are which 2 compounds are mixed in what ratio to form this azeotrope, and the azeotropes will be having 400 series. Okay. So these were all discussed in lecture number 23, and in lecture number 24, we discussed the different types of modifications. First of all, same as our Rankine cycle, increasing the condenser pressure. So in Rankine cycle, we are actually decreasing the condenser pressure and seeing here we will be seeing we saw the effect of condenser increasing the condenser pressure, then decrease of evaporator pressure, and somewhat flashing and cascading. This all were discussed, and I think we'll be solving one of the numerical on flashing. So that will mostly clear your basics on flashing. And increasing the condenser and the increasing the evaporator pressure are very simple, and I think that can be understood. Okay, cascading system was discussed in the last class as it is a combined cycle. For example, there will be 2 fluids, 2 refrigerants being operated in a different pressure and temperature ranges, and the evaporator of the topping refrigeration cycle will be acting as a heat rejection medium for the bottoming cycle. For example, the condenser of the bottoming cycle will reject the heat to the evaporator of the topping cycle. Okay, that is all about cascading. So these were all discussed in lecture number 22, 23, and 24. Based on this, of course, we'll solve few numericals and also few multiple choice questions. Then in lecture number 24, 25, we discussed the vapor absorption refrigeration system. Now, first of all, the first and foremost thing that needs to be understood that this is a thermally driven cycle. Thermally driven cycle means here earlier case in VCRS, the work input is generally in case of high grade energy. High grade energy input in case of VCRS. Okay. So that is why you will find that COP will be mostly more than 4. So generally nowadays the refrigeration VCRS system is above 5, and you can find that COP is going to 10, even 10 also. But mostly you will find average it will vary between 5 to 7. Okay. Now it is a thermally driven cycle. That means it is taking the low grade energy. Now, based on low grade energy, of course, the COP will be lesser. And for single systems, as far as this scope of this course is the scope of this course is concerned, it will mostly see the single stage systems. Even there are double stage and triple stage, but the highest efficiency that you can find in such absorption refrigeration system is around 1.3. But for single stage system, it will generally lie between 0.7 to 0.8. Okay. Now, what is the working principle of such refrigeration system was that the cycle will be having the same condenser, expansion valve, and the evaporator. So this thing doesn't changes. And here the working fluid, there also the working fluid was circulating through this. Here the working fluid is, if you see in this part of the cycle, it is only NH3. So the NH3 comes from the ammonia, passes through the condenser, expansion valve, and the evaporator. And both of these work at a different pressure. If this is pH, this is PL, at a different pressure and the corresponding saturation temperature. But the compressor is substituted by this system. That is the rectifier, the absorber, the regenerator, and the generator. Okay, this whole system is this replaces that of a compressor. Now, what is its function? If you see any absorption, any formation reaction, as I've already said, absorption is a formation reaction. That is NH3 plus H2O will react to form NH3H2. Okay. So this is a formation reaction. Thus, it will be an exothermic reaction. Thus, it will generate heat. So the heat that is generated, you can find out that the water is used to cool this. That heat has to be taken out. Okay. Now, once this solution is formed, it is pumped. Now, this is the pump. As this is a solution, so we don't need any compressor here. We use a pump. Okay. Now this pump goes and passes through the regenerator. Now, why this regenerator is there, we'll be discussing in a while. Now it goes to the generator. Now in the generator, what will happen is this NH3.H2O will be separated to NH3 vapor, because as I already said, this part of cycle will only deal with NH3, only ammonia gas. Okay. So here NH3 and water will be aqueous solution of this aqueous solution of ammonia and water will be separated. And how that separation is done? Whenever there will be a breakage of bond, we need to provide some energy. Okay. Okay. So this energy is provided even by a solar energy or even any heat source. And this is generally taking place at around 120 to 140 degrees Celsius. Okay. Now, as this energy is provided, the solution breaks down into NH3 gas and H2, ammonia gas and H2. Okay. Now this H2O is returning back through this generator, and here the temperature, as I already said, it is 120 140 degrees Celsius, and this generally will take place at around 30 degrees Celsius. Okay. 30 degrees Celsius. So thus, when it goes from here, this solution goes at 30 degrees Celsius and this solution comes at 120 degrees Celsius, there will be some exchange of heat, and we want this to take place so that the lesser amount of heat is required to break this bond between ammonia and water. That is why, to increase its thermal efficiency, we generally what we do is pass it to the regenerator, and this regenerator's function is to exchange the heat from the higher temperature aqueous solution of ammonia and water to the lower concentration. To the no, from the water to the ammonia solution. Okay. Now, even though the generator here, the energy is enough to separate the ammonia and water, there will be still some water molecules will be attached to the ammonia gas, and thus there is a rectifier which is used to remove the remaining water vapors. and thus then the pure NH3 will be coming through this cycle. Okay. So I hope the working principle is very clear. And here you will find that the COP you will find as QL. Where is the cooling effect taking place? Is the evaporator. And what is the heat input? What is the input that we are providing? First is the solar energy. Let us say that is Qgen plus the work of the work for running this pump in between these two pressures. So the pump work will obviously very less, and generally you will find that it is QL by Q generation. Okay, that's all. So that's all was discussed in this lecture, and also LIBR system was also discussed. This is also another type of vapor absorption refrigeration system, and I hope you will refer those lectures and you will try to understand. Okay. So now we'll solve few questions based on these lectures, and I hope you have followed all the lectures before this, all the lectures by the instructor, and I have just tried to briefly provide the summary of the lectures that were covered. And I always request you to go through those lectures for better understanding. Okay. So the first question, are you able to hear me?
Yes, sir.
Okay. So the first question goes like this: among the following, which one is identified or are identified as the biggest practical hindrance of the reverse Carnot cycle working with a condensable vapor as the working medium? So I'm giving you 1 minute. Think about it. Think about what are the key terms that you are looking for, and based on that, you will try to understand.
All the above, sir. Because compressing a mixture of liquid is easier, but liquid and vapor is difficult. Maintaining the temperature as constant while heat absorption and rejection, that is also difficult for us. That's why here all the above.
Okay. So no, the answer is actually the compressing a mixture of liquid and the vapor. So the biggest practical hindrance it is asked. That is what I referred. You have to see what are the keywords. First of all, the one of the keyword is biggest practical hindrance for the, and the second is the condensable vapor. Condensable vapor means there is a phase change process taking place. Now, when there is a phase change process, we know that isobaric and inside the dome, the isobaric and isothermal curve will be same. During the phase change, these two curve will be same. Yes or no?
Yes, sir. Yes, sir. Absolutely, sir.
Yeah, but in a reverse Carnot cycle, this all takes place inside the dome. That is why this is not the main hindrance that we are facing, and the only thing that we are going with in the case of a modification, if you say from the reverse Carnot cycle to the vapor compression cycle, the only thing that we are the first and the foremost thing that we are going is this isobaric. We are changing from this isothermal to isobaric heat rejection. That in case of condenser, as I already covered here. In case of condenser, you will find that the heat rejection generally takes place at a constant pressure and not constant temperature. Okay. Because we are handling superheated vapor, that is why mostly you will find it is taking place at a constant pressure. And heat rejection at constant temperature, this anyway, whether you refer it to as a vapor compression cycle or a vapor or a reverse Carnot cycle, in both the cases it is at constant temperature, because we are not going outside of this curve. Thus the curve will be always isothermal or isobaric, it doesn't matter. So the correct answer is option A, compressing a mixture of liquid and vapor. Okay, got it?
Yes, sir. But by the meantime, if they are generically asking what are the drawbacks or otherwise practical difficulties for a reversed Carnot cycle, in the sense by that time whether we can consider option B as well as C, sir. So instead of saying that biggest practical hindrance, simply saying that it is a drawback or otherwise why it is not feasible. Like this, if they are posting the question, means by that time whether we can consider all the above, sir.
No, in that case also option number B you cannot consider, Because as I already said, VCRS also takes place at constant temperature only. Heat absorption at constant temperature. The evaporator doesn't work for it. The evaporator that you see works inside this dome. So the isobaric and isothermal are in line. So you never find that that is a problem in case of evaporator. Okay, but in case of heat rejection at constant temperature, you are absolutely right. Even one of the hindrance, and for that only, as we are not able to other than compression, we cannot handle both liquid, both the liquid plus vapor mixture in case of such cycles. That is one of the other hindrances. But the biggest hindrance is the option number A. Okay.
Okay, sir. Okay, sir. Got it, sir.
Now, question number 2, for an ideal refrigerator R and an ideal heat pump HP working within the same temperature range, which of the following relation is true? That is very easy. Just tell me what is the answer.
Yes, sir. COP of heat pump, which is equal to 1 plus COP of refrigerator. Option A is
correct. So that is perfectly correct, and this has already been derived in the lectures. But still, if you want, just sometime I will do. So let us say this is TH, this is TL. So here in both the heat pump and in refrigerator, you will find that the heat is transferred from the low temperature to the high temperature. That is why we need a work. So this is Q1, this is Q2. So first of all, let's find out what is the COP of heat pump. COP of the heat pump is what is the desired effect? We want this space to be heated. So it is Q2 divided by W in. Now in place of Q2, you can write as Q1 plus W in by W. So we can write as 1 by 1 plus Q in. Sorry, it's Q1 by W in. This Q1 by W in can also be written as COP of the refrigerator. That is why you find this answer to be correct. Okay. Question number 3, which process or processes of a reversed Carnot cycle are modified in the sorry, it is not it is in a standard saturated single stage cycle. Yeah, that can be referred to question number 1, and you can answer this question. Which process for a reverse Carnot cycle are modified in a standard saturated single stage cycle? Tell me.
heat rejection and expansion, sir.
Heat rejection and expansion. Okay. Okay, you are absolutely right. So the answer is heat rejection and expansion. In case of VCRS, you will find that we go for heat rejection is generally we see takes place at isobaric condition. So that is one of the modification that we do. And the second modification is expansion. In a reverse Carnot cycle, you will find that turbine was used. Okay, turbine was used, but in case of a SSS cycle, you will find out
Throttling.
yeah, throttling. So the correct answer is option 3, D. Question number 4, a heat pump uses ammonia with low temperature of 25 degrees Celsius and a high pressure of 5 megapascal. If it receives 1 megawatt of shaft power as input, then the amount of heat transferred at high temperature is dash megawatt. Can you solve this question? Right.
Yes, sir. Yes, sir. Doing, sir. I have tried, sir. I would like to verify my answer again. First of all, I have constructed the heat pump diagram. So here, cold temperature is 25 degree, low temperature is 25 degrees Celsius, and high and the heat source. I mean, warm environmental condition. They have given us 5 megapascal. So for this, the corresponding saturation temperature I have referred from the from this table. It is around 5 megapascal, 50 bar around 88.85 degrees Celsius, sir. So low temperature is 25 degrees Celsius, high temperature is 88.85 degrees Celsius. First of all, I consider this act as a reversible condition. COP of heat pump, which is equal to TH divided by TH minus TL. I have calculated the COP of the heat pump, and then in general COP of heat pump, which is equal to desired effect divided by work input. So here work input is given as 1 megawatt. I have roughly obtained around the desired effect is 5.67 megawatts, sir. I would like to check it again, sir. I would like to verify my steps are correct.
Okay. Okay. So yes, the approach is totally right. So first of all, what are the things given? The low temperature is given, that is the TL is 25 degrees Celsius. So you have to convert it whenever handling anything with in Carnot cycle or Carnot for Carnot cycles formula, always convert it into Kelvin. So it will be 298 Kelvin. Then TH, we don't know what is the TH value. Sorry, this is TH value, but in case of as we are handling with ammonia, so TH can be thought of as the saturation temperature at the high pressure, that is 5 megapascal. So TH is the Tsat at 5 megapascal. So using this table, you will find that at 5.88 megapascal, we have a T saturation as 96.9 degrees Celsius. Similarly, if you see the temperature, if you see 3.87 megapascal, the saturation temperature that we see is 76.9 degrees Celsius. Okay. Now, as I already discussed the interpolation that in the last class, I think from using that we can find out what is the saturation temperature for 5 megapascal. So using that interpolation formula, we'll find out how to find out that one. So first of all, we have to find out the temperature. So the numerator, that will be temperature. So 96.9 minus 76.9 divided by 5.88 minus 3.87. So for this much variation in the temperature, we have this much variation in the pressure. But how much pressure variation we want? We want 5 minus 3.87. Now calculate this, how much? We'll find it as 11.22. 11.243 degrees Celsius, and this you have to add with the corresponding to the saturation temperature at 3.87, because with respect to that only we have taken the difference. So it is 76.9, 88.14. Okay, degrees Celsius. Then convert it into Kelvin, plus 273.15. We get 361.3 Kelvin. Okay. So once you got this temperature, we now have a TH. TH is 361.3 Kelvin. Now the COP, considering to be Carnot COP, is TL. Sorry, it will be TH by TH minus TL. So it's 361 0.3 divided by 361.3 minus 298.
$5.72, sir.
Yeah, 5.7. Then if it receives 1 megawatt of soft power as input, so W in COP can also be written as QH divided by W is equal to 5.7. So obviously the W is known to us 1 megawatt. So you'll find that QH is 5.7. Okay. Okay, it is asking in megawatt, so it is 5.7 megawatt. I think you also got this answer, right?
Yes, sir. Yes, sir. 5.62. I got it because by the time interpolation, I obtained around 8.85 degrees Celsius. Now there is a change, small change. Now almost answer is same, sir. Thank you, sir.
Now going to the next question. Which among the following is not an effect of reducing the condensate temperature of a standard VCRS while maintaining a constant evaporator temperature? Yeah. So this was discussed in the lectures, but we haven't discussed this in our summary discussion. But try to find out the answer of this question. But we'll surely discuss it now.
If we are reducing the condenser temperature, by that time, work in the compressor will increase, sir. By the meantime, refrigeration effect is going to reduce. The temperature at the end of compression is at higher side. All put together, the COP value will comes down, reduce. COP value reduce. That's why here not an effect of reducing the condenser temperature is asked. So that's why increase in amount of heat rejection. That may be the choice.
Okay. We'll see what is the answer. So first of all, on such type of question, try to make the cycle so PS or even in PHP, PH graph you can also follow, but you will find somewhat like this. This is the first case. 1, 2, 3, 4. So which among the following is not an effect? So first of all, this is one of the keywords, effect of reducing the condenser temperature is reduced. So what we are doing is we have now the temperature is this one. Okay. And but it has to reach here. So the updated one is 2 dash 3 dash. This 4 dash. Okay. Now you tell me, maintaining the constant evaporator temperature. Okay. So first of all, the option 1 is reduction in the compressor work. So does that reduction, is there the reduction in the work, compressor work has reduced?
Yes, sir. H2 minus H1 is higher than that of H2 dash minus
So
H1.
earlier it was H2 minus H1. Now it is H2 dash minus H1 dash. H1. So what is the effect? So you will find that there is a reduction. There is a reduction. So the option, this is one of the effect. Then comes the reduction in the maximum cycle temperature. Of course, this is right, because as the pressure will reduce, of course, the corresponding T saturation has to reduce. So the maximum temperature is reduced in this case. So this is also one of the effect. Now increase in the COP. Now let's find out whether there is an increase in COP or not. If you see earlier if you find out the pressure, you will find out the what is the cooling effect. Cooling effect, if you see, it is H4 dash minus, sorry, H1 minus H4 dash. But now it is H4 dash H1. Sorry, I just confused you. So in the first case, it was H1 minus H4. But now it has changed to H1 minus H4 dash. In which case do you find there is a large variation in the enthalpy? It is, of course, the second case. So one case we are finding it out is the cooling rate is increasing. The rate of rejection of this heat is increasing. So cooling effect has increased. COP is QL by W. So we found out that W has reduced, QL has increased. So the overall effect is COP will increase. So this is also one of the effect that we are seeing. But the other thing is increase in the amount of heat rejection. So is this one of the effect? No, if it is not, okay. It is not the one of the effect. If you see increase in the amount of heat of rejection. What is the amount of heat that is rejected?
Heat rejected in the condenser side, sir.
Correct. So earlier it was Q rejection was H2 minus H3.
H3.
And now it is QR dash is H2 dash
minus H3 dash.
So in which case do you find there is more heat rejection? This was the case earlier. This is the case now. Okay. Mostly you cannot comment on this, to be very honest, but mostly you will find that the amount of heat rejection will reduce, because if you see QH, what is QH actually? QL plus W. Okay. Now if you see QL, we are finding out that QL is increasing. QL is increasing and W is reducing. So the ratio in which this we'll see whether the W increase in the W is more or decrease in the QL. Sorry, increase in the QL is more or decrease in the W is more. Based on that only we can comment. So this is also is of course not an effect. Directly we cannot say it. We have to analyze to find out whether the heat rejection will increase or decrease. Okay. So the based on elimination we can tell the correct answer is 5D, increase in the amount of heat rejection. Okay.
Okay, sir.
So this is another numerical. An ideal R12 based VCR system is operating with a condenser temperature of 40 degrees Celsius and an evaporator temperature of 0 degrees Celsius. The state at the exit of the evaporator is of saturated vapor and the exit of the condenser is of saturated liquid. Then the COP of the cycle is. Try to solve this question. If you have solved, you can tell me the approach.
Yes, sir. I've tried, but I would like to verify the answer because I need that CP value and all. First of all, I have drawn the pH as well as TS diagram of a simple VCR system, and then calculated that the enthalpy value at the exit from the evaporator, that is at the saturated condition, vapor condition. That's why H1 equal to Hg. I have taken the value directly. By the meantime, S1 equal to Sg. that is also taken for a low temperature, 0 degree Celsius.
Okay.
Here entropy is constant. That's why S1 equal to S2. That S2 is at a superheated condition. Entropy S2. For this, I have referred that condenser temperature. Condenser temperature at 40 degrees Celsius. This S2 is at a superheated. That's why S2, which is equal to Sg plus Cp into T Cp into ln of T superheated by T saturated.
Correct.
For
Because it is
this, I need
constant.
the test. Nice. Cp value is required. So from this, I calculated the exit temperature from the compressor, and then calculated the enthalpy value at the exit from the compressor. H2 I have calculated, and followed by at condenser temperature enthalpy HF value I have taken. Throttling enthalpy is constant, so H3 equal to H4. So likewise, what I have attempted, and then I got the final answer is 5.6, sir. COP. Anyway, I would like to verify it again. The property table. Yes,
Yeah.
sir.
Yeah.
The,
Tell me.
the property I have referred. I have not, by the time I have not having any kind of refrigeration table. I referred from internet, and then I have taken the value, sir.
Of
CP
CP.
liquid I have taken as at 0 degrees Celsius 0.928 kilojoule per kilogram Kelvin. CP vapor taken as 0.633 kilojoule per kilogram Kelvin. So by the meantime, 40 degrees Celsius at the condenser temperature, CPL I have taken as 1.030, CP vapor condition 0.762 kilojoule per kilogram Kelvin. So if it is right in the sense, the answer may be somewhat closer to correct. Otherwise, I need to do the calculation again, get the exact value here, sir.
Correct. So your approach is completely correct. And if you don't have the value of either the enthalpies or even, or if at all CP also, then you cannot able to solve this question. So there are two approaches. The second approach is what I have followed to find out the answer of this question. So the first approach that you have followed, I will try to explain. So first of all, in such type of question, in any of the applied thermodynamics question, always remember to start with drawing the cycle diagram. So in refrigeration, mostly this curve will help you, pH curve, the pressure enthalpy curve. So this is the thing that you will find out. This is the pH curve. If you don't know the pH curve, even TS will also do, not a problem, but mostly try to follow pH curve. That will be helpful for you. In this case, the only difference that you will find is the compression will be a straight line. It will go to the superheated state. Then it will come back to its pressure. Then this curve is a irreversible curve. So the generally dotted lines, you can also, for your purpose, you can connect it to a continuous line, and that will be not a straight line. Okay. So first of all, in this case, very simple formula, you know, that is the COP is H1 minus H4 divided by H2 minus H1. Now you have to find out the enthalpy at all these points. So H1, if you have the CP value, for example, the first approach that I am telling is if you have the CP values. If you have the CP values, H1 can be found out at CP into this T1. So CP vapor or CP gas. So CP vapor into T1, that is at T1, the temperature is 0 degrees Celsius. So you will find out, convert into, check what is the CP value. If it is in Kelvin, based on that, change the temperature into 0 degrees Celsius. But this is where I would not like to follow this approach. But as you have discussed, so I will also explain other students who are attending these lectures, if they are going through this approach, what are the problems or confusion that they might face. First of all, the confusion that you will face is the 0 degrees Celsius. So if you multiply, if you take it in temperature scale, because generally we have a tendency that Cp we multiply with the temperature difference. So that is why we also we multiply even that multiply even the this one even the Celsius centigrade degree Celsius also centigrade degree temperatures also. So in that case, you will find that H1 is 0, which is not the case. Okay. So you will convert it into Kelvin, 273 Kelvin. Then what are the other things you can find out? H4. What is H4? This is isenthalpic line. So H3 will be H4. So H4 is equal to Cp liquid into T4. Or even you can find out if that is difficult, you can find out Cpl into T3. Okay, because this is completely this is a completely liquid line. Okay. So you'll get some values. Then the next thing comes is the H2, where you will face the most challenging task. H2, because H2 you have to find out, as this is an isentropic line, you have to equate S1 is equal to S2. For sure, you will find that the S1 values, let us say this value is somewhat 7.3. So the you have to see that at this pressure, whatever the pressure corresponding P saturation pressure at 40 degrees Celsius, P saturation at 40 degrees Celsius, you will find out that the SG at this pressure and temperature will be lesser than 7.3. This is just a value I have taken. So you have to go for superheated table, and mostly in refrigerant you won't find out the superheated table. But that is why what you have to find out is this: what is the temperature at T2, and that, as rightly said, the temperature need to find out how to find out the temperature. You need to use the formula Sg plus. This is a what is this process? This is a constant pressure process. Constant pressure process, and the temperature is increasing. So mostly you will find out ln Cp ln T2 by Tg. Okay, Tg at this 40 degrees Celsius. And of course, that is 40 degrees Celsius only. And based on that, you will equate to S1. And here you would be knowing Cp vapor, of course. Sg you have no, Cp vapor you know, and you can find out T2. Follow this method only when the value of Cp and Cv are given. Now, once T2 is done, then you can find out H2, Cp vapor by T2. And once you find all these enthalpies, you will find out the COP, okay? And based on his approach, I think he got somewhat around 5.6, right?
Yes, sir. 5.6.
Yeah. So, but the second approach that I follow is, if you need to have a pH chart for this refrigerant R12. This table you won't this chart you won't find in the Sengel and Bose, because only R134 chart is given. You don't find it, so you have to look for the internet. I have provided in this slides. This is the pH chart for the R12. Okay. Now this is pressure, and based on pressure you will also find the temperature also. These are the temperatures. These are the temperature. These are the constant pressure lines. Constant pressure lines. Okay, and these are the constant enthalpy lines as the verticals on the constant enthalpy lines, and this is the isentropic lines. So very easy to refer this table. The slanting lines are the constant entropy lines. So why this is easier, you should just see. So what are the temperatures that we are handling? That is 40 degrees Celsius and 0 degrees Celsius. Okay. So what is, let us say this is 40 degrees Celsius. You need to draw a straight line on this chart. This is somewhat like this. This is the condenser line. Then the evaporator line is 0 degrees Celsius. This is the 0 degree Celsius. Okay. From here, what are the points you need to find out? First of all, this is our 1 point, point number 1. Okay. Then the next point is isentropic lines you have to follow. Isentropic lines follow like this. Okay. You have to go till the condenser pressure. You join it here. So this is our point 2 line. Okay. Then you come, this is our condenser line. You have to go to the saturated liquid line. This is the 3 line. Then you have to come straight. This is our fourth point. Okay. So this is our cycle if drawn on that chart, and based on that, you can find out what is the COP. COP is H1 minus H4 by H1 minus H2. So find out what are the points. If I say H1, what is H1 enthalpy? So it's a bit tough only. If I take it, it is little bit more than 350 line. This is the 340. I hope you can see the screen. It is a bit clear. Try to zoom. This is 340. This is 360. So it is more than 350 line. So let us consider it to be around 350, 352. So H1 is 352 kilojoule per kg. Then the next thing will be coming is H2. This is our H2 and it is slightly more than 370 line, and it's based on your judgment. It is around 373 kilojoule per kg. Then comes the H3 or S4 point. H4 is somewhat lesser than 240. Consider it to be 238 kilojoule per kg. Find out. So it is 352. 352 minus H4 is 238. Then it is sorry, it is H2 minus H1. H2 minus H1. So H2 is 373 minus 352. I am getting 5.42. Okay. I think you also got 5.6, somewhat close based on your.
Yes, sir. 5.6 I have obtained, sir. 5.4, sir. Okay, 5.42.
Yeah. So the correct answer can fall between these two range. And unless it is given if the curve or the CP value, we cannot solve this question. Sometimes you will find out that the specific values are given. In that case, follow this approach, first approach. Otherwise, this is the second approach. Which is pretty simple. Coming to the next question. An ideal VCR system works with R22 as the working. So here also there will be two approaches. And based on your thought process, so you can use whatever approach you like. Either you find out the CP value for this R22 or directly you can refer the chart. I have provided the chart here. You can refer it. Okay. So an ideal VCR system works with R22 as the working medium and with condenser and evaporator temperature of 40 degrees Celsius and 5 degrees Celsius respectively. It has been designed to produce a cooling capacity of 40 T. It is now made to operate with an evaporator temperature of minus 35 degrees Celsius. If the condenser temperature and the volume flow rate of the refrigerant remains identical. So this is another key information. So what is the cooling capacity? Modified cooling capacity. So based on just your judgment, try to tell me whether the cooling capacity will increase or decrease.
Actually, sir, here volume flow rate of the refrigerant remains identical in the sense volume flow rate which is equal to mass flow rate into uh, specific volume. So here volume flow rate is kept constant in the sense I have not solved this problem. I am thinking that the same capacity only what will takes place because here COP will decrease because evaporator temperature is minus 35 degrees Celsius.
Yeah.
Work input is so high, so work input increases, and then obviously COP value will decrease. But in the meantime, your volume flow rate is kept constant in the sense that to maintain the same volume flow rate, we need to adjust the mass flow rate. So that's why I thought that so here almost the same cooling capacity will take place.
Okay, but for that you need to have the density also,
Yes, sir.
because that is
Yes.
the thing that won't change. Okay. So the considering question to be very simple, the volume flow rate is equal to the mass flow rate. We don't because then we'll be having needing more number of inputs. For example, as you are saying, you are absolutely right. If you consider the volume flow rate to be constant, that means it's not mass flow rate. Mass flow rate means m dot will be constant, but in this case, it is given that volume flow rate has to be constant. That is q dot, which is mass into density. Okay, in this case, to manage this to be same, we have to, the mass has to change considering that density is constant, which is like very complex thing. Complex, we don't know what is the density, and getting these values are also difficult. So for this question, unless mentioned, consider volume flow rate and mass flow rate to be same. Okay, so consider that the m dot is constant and also the condenser temperature is constant. Okay, did you get it? Why I said like that? Your approach is perfectly right, but for that you need to have additional information which is very difficult to find. Okay, with considering this question has been given to you with no other values. Okay.
Okay, sir.
Yeah. So, so first of all, you are absolutely right. The evaporator temperature has reduced. Earlier it was 5 degrees Celsius. Now it has reduced to T dash has reduced to minus 35 degrees Celsius, which is a huge reduction. Huge reduction. And the temperature of the condenser is constant at 40 degrees Celsius. So as I already said, the two approaches can be followed. For that, you need to have CP values. Then you can find out what is the change. If you have the CP value, the same approach you can follow will be if this is a TS plot, this is somewhat will look like this. Earlier it was let us say from here to here. Now it will be the condenser temperature is same. So it will look somewhat like this. Sorry, this is 1, 2, 3, 4. This is 2 dash. This is 3, 4 dash. Okay. So this is the line that you will follow. Okay. So based on that, you can find out what is the 2 dash temperature. Again, that will be even a more difficult task to find out 2 dash, because you have to take S1 and the S1 value you have to find out, and you have to equate with Sg plus Cp ln T2 dash by Tg. Tg at this pressure at 40 degrees Celsius. Okay, for this refrigerant, that is a tedious task. After T2 dash, then you have to find out H2 dash. Then only you can find out the COP. And if the thing this in this question, it is only asking the cooling capacity, that is m dot into H1 minus H4 dash. You have to find out this value. What is this value? And the value that is given is m dot H. Okay, so this is 1 dash. So this is 1. H1 minus H4 is given as 40 TR. So convert it into kilowatt. Okay. So this is the value that is given. You have to find out what is m dot. Because H1 and H4 you know, or you have to know it. Like if Cp and Cp vapor and Cp liquid you have, you can find out what is the value of H1 and H4. And from that you can find out m dot. And once you know the m dot, you can find out H1 and H4 dash. Okay, H4 dash doesn't change. It will be same as H4. Only thing you need to find out is H1 dash. Okay, so that will help you to find out the answer for this. Now
Yes, sir.
the second
In
Yeah,
this
tell me.
approach, I have tried, sir. Assumed that taken the value from the internet. Then at last, for the second case, desired effect, which is equal to 39.74 kilowatt. 39.74 kilowatt.
Kilowatt or TR?
TRs, ton of refrigeration.
Okay, so you are getting the 39 point. You are getting 39 point. How much? Could you repeat it?
39.74 kilowatts. Kilowatt only. Anyway,
Kilowatt?
I will check it out, sir. Kilowatt. No, it is wrong.
It is not possible.
Yes, sir. Yes, sir. Not possible.
So this is not possible, but anyways, that is the approach you need to follow in this first approach. The second approach is
139.74 kilowatt. 139.74 kilowatt. 139.74 kilowatt. So almost that is also 40 ton of refrigeration. That is equal to 140.8 kilowatt. For the new case, I am going to get very closer to what 140.8 kilowatt. That is nearer to 40 ton of refrigeration only. I have obtained.
So mostly this is because of the the values of the Cp that you are referring. Okay, that might not be right at the particular pressure and temperature, because Cp values for this will change. Okay, so best way that I always say is referring the pH chart if these values are not given to you. Okay, see the simplicity where if you follow the this Freon 22 pH chart. So earlier it was 0 degrees Celsius. What are the values you need to know? Just you need to see, okay, this is first one of the point you need to carry, and the second is 40 degrees Celsius. So whether it was 0 or 5 degrees, yeah, sorry, it was 5 degrees Celsius. So the 5 would fall somewhere here. Okay, this is 5 degrees Celsius. So this is the point you need to focus, point number 1. And the other point is this one, point number 3. So it is somewhere around 260. Sorry, 220, 240, and this is 260. So this will be somewhat around 250. So it is 250 kilojoule per kg. Okay. Now this line doesn't changes even though it goes to 35 minus 35 degrees Celsius. This is 30. So minus 35 is somewhat here. Okay. Minus 35 is somewhat here. So that line stays the same. The only thing that changes is this one. Okay. So it is, if I'm not wrong, this value is somewhat in between 280 and 380 and 390. You can take it to be 385 kilojoule per kg. And this value, one value is somewhat around 410, near to 410. Let us take it as 408. Okay. So calculate m dot. So it is 408 minus 250 is equal to how much? 40 TR. 40 TR is 3.5 kilowatt. Find out in kg per second how much you're getting. somewhat around 0.88. I'm getting 0.88 kg per second is the flow rate of the refrigerant. Then the second thing is the m dot modified is 0.88 into 385 minus 250. We get 119, somewhat around 119.62 kilowatt. Of course, this is kilowatt. And when you divide it by 3.5, you'll get 34.17. Okay. Did you understand?
Yes, sir.
So the next question, use of a regenerator in the absorber circuit of a standard VRS enhances COP by, yeah, tell me. Very simple question. We already discussed this during our summary revision.
Reducing generator heat requirement. It is one
Correct.
kind of heat recovery system.
Correct. Absolutely correct. The correct answer is option B, because if you remember, I go back, you might have forgotten which one is regenerator. So the regenerator is this one, the heat exchanger, where the high concentration fluid is going at a low temperature, and the low concentration fluid is coming at a higher temperature. So they will exchange the heat in between themselves, and thus you need to have lesser heat to be provided at the generator. Okay. So the correct answer is reducing the generator heat requirement, and that will enhance the COP, because if Qgen reduces, of course the COP will increase. Then the next thing, question number 9. An organic refrigerant, inorganic refrigerant is represented as R7XX. Here XX represent what? Very easy.
Molecular weight, sir.
Correct. So in inorganic, as I already said, they are represented as 7XX, where XX is the molecular weight, generally for ammonia and all. Then the next question comes is question number 10. The chemical formula for R12. So this is an exercise. Try to find out what is R12. First of all, in such questions, always focus on how many digits are given. So it is 2 digits. So there cannot be any refrigerant starting with starting with 1 and having two digits. So considered as 0, 1, 2. So R012. So first of all, this is X, this is Y, this is Z. So 0 means X is the number of carbon minus 1. So the carbon amount is 0 plus 1 is 1. Hydrogen amount is Y minus 1. So it is 1 minus 1. It is 0. Then Z is the fluorine. So fluorine is 2. So this is a single carbon, that means 4. This is an alkane based refrigerant. Okay. Alkane based refrigerant. Find out if it was CH4 means 4 bond it has to be. So there is no hydrogen. So it is CF2 for sure. The other two will be acquired by chlorine. Okay. So the correct answer is CCl2F2. Dichlorofluoroethane. Okay. Got it?
Yes, sir.
Now the next question. Such question was solved in the class also, but there the values are already given. That is why I want to rediscuss that question.
Sorry for the interruption, sir. Sir, in the previous R12 chemical formula calculation, for example, in the chlorine content, number of chlorine, which is equal to, whether we can use that formula, sir, 2 into X plus 2 into minus Y minus 1 minus Z. 2 into X plus 1 plus that formula also we can use, sir.
Yeah, no problem. You can use that. The only thing is carbon can form four single bonds.
Yes, sir. Yes.
So based on if there are two fluorine, we know that it has, and
Yes.
it doesn't have any
Remaining two is
hydrogen.
yes.
So what is the thing that is left?
Chlorine only. Okay, fine, sir. Fine, sir. Thank you, sir. Thank you.
Yeah. So similarly, you can find out what is the formula for R1234 YF. This generally this refrigerant you will be finding in your even I have seen some of the domestic refrigerant being used using this domestic air conditioning system using this refrigerant R1234 YF. YF of course is the ice telling about the isomer. What is where is the where is this fluorine attached? Because the fluorine the chemical structure is very different from the way we are seeing. Uh, I cannot explain more about this chemical structure. Sometimes you'll find out fluorine here, and sometimes you'll find out fluorine here. For a chemical expert, these two are different. Okay, so they name it using a different set of series like YF or something. That is why this neglect this one. Find out for R1234. Okay, and then you can find out this refrigerant where it is being used. Okay. You can see your even your ACs in your ACs rating chart. Rating chart, you will find out what is the refrigerant. You can see in the backside of the AC in your room that you see. For example, this is the room. This is the evaporator that you see, that split AC type. I'm talking about that. So this is the evaporator. The coils will be outside, and that on which there will be a fan rotating. This is the condenser. So on that condenser only, this chart you will find out. Try to locate it and find out what is the refrigerant being used in your ACs. Okay.
Okay, sir.
Yeah. So the next question, this question has already been discussed in the class. So I want to rediscuss it so that I hope the how to find out those enthalpies were not discussed because the values are already given in that question. That is why I have changed the values of the pressures so that you can yourself calculate the values and find out what is the answer for all these questions, and that will be even a practice for you as well. I want to discuss that, but the solving will kindly do it at your as your homework. And if you face any problems, just write to me. I will be providing you the solution. So
Okay,
the
sir.
first is, as I already said, use pH plot. So here it is R134. First of all, R134A. In this case, we have the chart in our Tangerland bowl. So this is a considered two-stage compression refrigeration system operating between a pressure limit of 0.9 megapascal. So it is 0.9 megapascal and 0.12 megapascal. So this is the minimum and the maximum. So this is the evaporator pressure. This is the condenser pressure. So our working fluid is R134A. The refrigerant leaves the condenser as a saturated liquid and is throttled to a flash chamber operating as 0.35. Okay. So there is a flash chamber. There is a flash chamber at 0.35 megapascal. So why is flash chamber used? What is the main purpose of using it? Tell me.
Splitting that liquid vapor, sir.
Then what will happen?
Uh, liquid refrigerant should not enter into compressor.
Oh, where is then what will happen if the liquid? Anyways, we are heating it here, no? We are providing it saturated vapor. What is the problem?
Sorry, sir. No idea.
Okay. So mostly why this is done, whenever, as I already said, whenever we go for compression, always the focus is to reduce the size of the compressor. Okay. And here you can see when we are going, when we are compressing the fluid, if for example, all the gases, if there is no two-stage compression, all the gases will be handled in between these two pressure ranges, and this whole of this volume of compressor has to be compressed to this pressure from 0.1 to 0.9. Just imagine the size of the compressor that you will be needing. Okay. In that case, what we are doing is we are separating here. We are separating here the fluid, because if you consider it a mixture of, let us say, you will find out 0.2 is the X. That means the 80% of it is 80% of it is the fluid. 80% is the is not sorry, fluid is both gas and is the liquid, and 20% is the gas. But which will give you the cooling? Whether liquid will give you the cooling effect or the gas will give you the cooling effect in terms of VCRs? We'll get it by liquid only. See. Okay. That is why we separate it, because the gas has no role to no role here in a VCRS system. We'll always get the cooling when the fluid will get converted to gas. That is the amount of HFG, or the vaporization, enthalpy of vaporization, that will only give you the cooling effect here. So we don't need gas, because the gas is there is not. If we provide more amount of energy to this gas, it will only get it to superheated mode. Okay. Do you understand why do we have a flash chamber?
Yes, sir. Yes, sir.
Yeah. So this is the question. So just name all the points. 1, 2, 3. This is 4. This is 5, 6, 7, 8, 9. Okay. So during the flashing, the part of the refrigerant evaporates and the vapor is mixed with the refrigerant, leaving the low pressure compressor. So this is the point where the refrigerant coming from the compressor 1. This is the compressor 1. This is the compressor 2. Okay. So this both. So at 3, the compressor, the fluid, the gas that is coming from the compressor 1 is mixing with the gas that is coming from the flash chamber. Flash chamber is somewhere at around here. Okay. Then the mixture is then compressed to the condenser pressure by a high pressure compressor. So that is the compressor 2. The liquid in the flash chamber is throttled to the evaporator pressure and pulls the refrigerator space as it vaporizes in the evaporator. Assume that the refrigerant leaves the evaporator as a saturated vapor, and both the compressor operate isentropically. Okay. So first of all, we need to find out in such type of question, whenever there, as I already said, whenever you're dealing with air refrigeration system, you have to find out temperatures, or the Brayton cycle, you have to find out the temperatures. But when we are dealing with vapor systems, vapor domes, you have to find out the enthalpy. Actually, in both the cases, you need enthalpy. But in case of air, we treat it as an ideal gas, and thus we multiplied Cp, the value which is well known. So we get it very easily. So that is why we only need temperature. But in case of vapor cases where we don't know the value of Cp, we need to find out direct enthalpy. Find out what is H1. I am referring to the table number. Just I will let you know the table. You find out all the points. Okay, I'm referring table A12 from table A12. Okay. First of all, what is the pressure here? 0.12. Look for 0.12 pressure. 12 megapascal. That means 120 kilopascal. So at 120 kilopascal, I am getting T saturation as minus 22.32. This is minus 22.32. What is the Hg at this point? The Hg that you get at this point is 236.99. Correct? Are you referring, or you can refer it later, to 36.99 kilojoule per kg? How did I calculate this? This is Hg at 0.12 megapascal or 120 kilopascal. Then comes what is the S1? Because this is an isentropic process, we need to find out what is S1. So S1 you will find it as Sg 0.94789. 0.789 kilojoule per kg Kelvin. This is also Sg at 0.12. Now 1 is done. How to find out 2? For 2, you need to find out what is the pressure here. So first of all, the pressure is 350 kilopascal. 350 kilopascal. Now at 350 kilopascal, if you refer the table, of course 350 kilopascal, the values are not given. After 320, it is 360. So even at 360, if you see, it is 0.9285 Sg at 360 kilopascal is 0.92856. 0.92856 joule per kg Kelvin. That means at higher pressure, the entropy is still lesser than the entropy at S1. That means we have this is in the superheated state. So find out Sg plus Cp ln T2. It's not T2, it's T, yeah, T2 by T saturation at 350 kilopascal. Now for this, by default, you have to take what is the value of Cp. Okay. You have to take the value from the internet, or you can directly, if such type of question is there, and if you have the R134 pH chart, you can also refer that. Directly you will find all that. Okay. From there, if you equate with S1, you will find out what is T2. Okay. That T2 will help you to find out H2. That also you have to do it by interpolation. This is a long question. I think you will at least take 15-20 minutes, half an hour to solve this question. Give it a try. Your basics will be even better. So once H2 is done, we can now start finding out the this one, the first bit, the fraction of the refrigerant that evaporates during the throttling. So we need to have, let us find out that, okay, we have need to find out the quality here. Okay, the quality here. So how to find out the quality? We need to do the energy balance here. That means whatever gases are coming, if I do the energy balance at 3, you do the energy balance at 3. At 3, that means whatever, let us say this X, the quality here is X. That means X amount will go to X amount from the flash chamber will go into this to this compressor inlet. That means what is its enthalpy here? That is the Hg. That is what I have named as 4. So X into H4 plus. And what is the other thing that is coming inside? It is this compressed. That is the H2. That is 1 minus X to H2. Because if X amount goes here and let us say 1 kg per second, 1 kg of amount was coming and X amount goes here. So 1 minus X will come here. Same as our feed water systems in the Rankine cycle is equal to, when they both will mix, they will form H3. You can understand it just by this. Let us say this is the compressor inlet, compressor 2 inlet. From here, the flash chambers, flash vapor is coming from below. The compressed vapor is coming. And both, they will be compressed together. They will be compressed to the higher pressure. What is the pressure? Let us say it is to 5. Now this is coming from, this is happening at 3. It is coming from 4, is 2. Okay. That's all. From here, you can directly find out. Only unknown that you will find out is x. Here you can find out x because h4. How to find out h4? H4 is hg at that pressure. H4 is actually the hg at 350 kilopascal. And h2 you have already found out. From here you can find out x. So the first bit is answered. This is how it was solved in the class as well. Then the amount of heat removed from the refrigerated space. How to find out that? Refrigerated space means it is asking QL.
Refrigeration effect.
Yeah. So it is asking H1 minus H9. So of course you cannot find out m dot. So consider it to be 1. So that is 1 minus x. So 1 minus x into H1 minus H9. So H1 you would have already found out. H9. H9 can be found out. What is H9? H9 is actually the HF at 350 kilopascal. Okay. So once that is done, you can find out the option B as well. Then the next thing comes COP. For COP, you need to find out the work input. So the same procedure as we found out T2, find out T5. Found out T5. How to find out? You have to equate S3 at S3 is equal to S5. And S5 will be nothing but SG at the highest pressure is I think 900 kilopascal plus Cp ln T5 by Tg at 900 kilopascal. From here you can find out T5. Once T5 is done, then you can find out H. Once all the values are done, COP is very simple for you. So QL by, remember to multiply the fraction x 1 minus x into what is the H1, H3 minus H1 plus the complete mass H5 minus H3. You will get your values. Try to find out this one. I think that will really clear your basics, and try to also, if you can get a pH plot for R134 from internet. If you get, try to solve it using reverse check with R134A, the pH plot. I will surely share the plot for these R122 and R22 and R11. Whatever questions we solved, I will share the PDF of that. You can use it for your purpose. Okay. So that's all for this class. For today's lecture. So if you have any doubt, you can ask, or we can close this class.
Yes, sir. Only one small clarification, sir. In the previous slide, we have done the energy balance. Energy balance at 3. Next slide, sir. So
Okay.
here x H4, 1 minus x H2, that H3, and the H3 is what lies between what the pH diagram between 2 and 4.
Correct.
2 and 4, sir.
Correct.
So how to get that H3 value, sir?
Okay.
Okay.
H3. Okay, for that you need to correct. It's a very good doubt. So S3 you need to have the value. Otherwise you cannot find out. You need to know the conditions at the exit of this. Correct. Absolutely correct. That is a good point. So for H3 you need to either it should be given, or the condition has to, or the temperature has to be given. What is the temperature at the exit of the feed? Sorry, the mix after the mixing of the flash chamber.
Yes, sir. Yes, sir. Okay, sir. Thank you, sir. Thanks.
Okay then.
Okay, sir.
Okay then. So have a good day. Bye.
Thank you very much, sir. Kind of you, sir. Thank you very much, sir.